Good morning, students. In the previous class, that is class 1 of the chapter Chemical Kinetics, already we cover the introduction part. What is the chemical kinetics? Depending upon the rate of reaction, the division of three types, that is very fast or instantaneous rate, moderate rate, and slow rate reaction, the classification. Then what is rate of reaction? It's a mathematical expression. Unit of rate of reaction. Then the various factors affecting rate of reaction and some numericals related to rate of reaction. Today, in class 2 of the chapter Chemical Kinetics, we will cover rate law and rate constant. What we cover in today class? That is a rate law, rate constant, and its characteristics. Rate constant and its characteristics. Then difference between or distinction between rate of reaction and rate constant. Then order of reaction, characteristics of order of reaction, types of order of reaction, unit of rate constant, molecularity of a reaction, characteristics of molecularity, and different types of molecularity. So let us discuss one by one. First one we discuss rate law. It is a mathematical expression which represents the experimentally observed dependence of change in molar concentration of reactant during the rate of reaction. That means in class 11 of the chapter Chemical Equilibrium, we cover one term that is known as law of mass action. What is the law of mass action? This law states that the rate of a reaction directly proportional to the product of molar concentration of reactant species, and each term raised to the power is equal to its coefficient represented in the rate of reaction. For a simple reaction, we discussed later, two types of reactions are there. One is known as a simple reaction or elementary reaction, and one is a complex reaction. Those reactions complete in one step, that is known as elementary reaction or simple reaction. Those reactions proceed through a number of steps, that is known as a complex reaction. So, for elementary reaction, for a simple reaction which complete in one step, for that, rate law is equal to law of mass action. But for a complex reaction, rate law differ from the law of mass action. In short, one says that law of mass action based upon theoretical concept, while the rate law based upon the experimental concept. For example, mark that if it is a elementary reaction, if it is a simple reaction which proceeds in a single step, AA plus BB give rise to product, where small letters are the coefficient and capital letters are the reactants. Then, if it is a simple reaction, then according to law of mass action are proportional to molar concentration of A to the power A, B to the power B, or R is equal to K, A to the power A, B to the power B. And this is also equivalent to the rate law. But suppose it is a complex reaction, that means it is completing more than one step. Then according to law of mass action, this one, while according to rate law, R is equal to K, A to the power N, B to the power N, where M is not equal to A and N is not equal to B. So, what is a rate law? I repeat again, it is experimentally observed the dependence of the molar concentration of reactant. This law states that the rate of a reaction is directly proportional to the product of a molar concentration of reactant species, and each term raised to the power is equal to the actual number of reactant species whose concentration is changed during the rate of reaction. That's why it is an experimental phenomenon. So by observing a simple balanced equation, no one able to represent what is the rate law expression, and it is based upon the experimental phenomena. But if the simple reaction, then according to law of mass action is equivalent to the rate law expression. So here we observe that R smaller represent the rate of reaction proportional to molar concentration. This square bracket of A is known as A and B represent molar concentration in moles per liter or active masses of the reactant species A and B. And here this K is known as a proportionally constant in rate law expression, which is known as rate constant or velocity constant or specific reaction rate. I repeat again, this K is known as rate constant or velocity constant or specific reaction rate. Mark that, I repeat this expression again, that is R is equal to K, A to the power A, B to the power B. So when molar concentration of A is equivalent to molar concentration of B is equal to unity. When molar concentration of all reactant species is equivalent to unity, then R is equal to K. Hence, from this mathematical expression, one is able to define the velocity constant or rate constant. That means the rate constant or velocity constant may be defined as the rate of reaction. The rate constant or velocity constant may be defined as the rate of reaction when all the concentration of reactant species is unity. Then we go through the characteristics of rate constant. Then we discuss the characteristics of rate constant. Characteristics of rate constant. 2 to 3 points are there. Point 1, it is the measure of the rate of reaction. The rate constant measure the rate of reaction. It indicates that higher the value of a rate constant, higher is the rate of reaction. I represent this one. That is, higher is the value of rate constant, higher is the rate of reaction. Point 2. At a particular temperature, each reaction possesses a definite value of rate constant. At a particular temperature, Each reaction possesses a definite value of rate constant. This value rate constant depends upon temperature. This value it depends upon the temperature. Its value increases with increase in temperature. Next point, it is independent of initial concentration of reactant. The value of rate constant not depends upon the initial concentration of reactant. Last one, its unit depends upon the order of reaction. It is very, very important. The unit of rate constant not fixed, it will vary depending upon the order of reaction. What is order of reaction? We discuss later. Next, we will make a comparison between rate of reaction and rate constant, or reaction rate constant, or velocity constant. Next, we will go through a comparison, go through a distinction between rate of reaction. Rate of reaction symbol is R, and one is reaction rate constant or velocity constant or specific reaction rate. While defining the distinction, we discuss first point always a definition. What is the definition? I repeat again. What is the definition of rate of reaction? That is R. Rate of reaction define a change in molar concentration of reactant species or product species with respect to time. While the rate constant is a mathematical expression, it is a mathematical expression represented, it is a proportionally constant which is represented in rate law expression and is equal to rate of reaction when the molar concentration of reactant species is unity. Point 2, that is, second point is the rate of reaction depends upon the temperature. Rate of reaction depends upon the temperature. The reaction rate constant or velocity constant also depends upon temperature, and it increases nearly double or triple for every 10 degrees centigrade rise in temperature. Then rate of reaction depends upon the initial concentration of reactant species. Initial concentration of reactant species, it is independent of initial concentration of reactant species. Next point, its unit rate of reaction, its unit is fixed, that is moles per liter per second, but its unit vary according to its unit depends upon, not fixed, depends upon the order of reaction. It is the difference between rate of reaction and a reaction rate constant or velocity constant. Next, we discuss about what is order of a reaction. Next we discuss about order of a reaction. Very important one. In the chemical kinetics, in this chapter, two terms is there. One is order of a reaction and one is molecularity of a reaction. It may be 2 mark or 3 mark. If in the question define order of a reaction, then we simply write the definition and mathematical expression. On the other hand, if it is 3 mark, write short notes on order of a reaction. Then we write the definition, mathematical expression, characteristics of order of reaction, then different types of order of reaction. Similarly, the molecularity we discuss later. If it is a 2 mark, simply write the definition. If it is a 3 mark, definition, characteristics and types of molecularity. First we discuss order of a reaction. It is an experimental concept. This concept based upon the experimental phenomena. That means, while going through the rate law expression, observe that for a general reaction, A plus B give rise to product. Then according to rate law, rate of reaction is equal to A to the power m, B to the power n for complex reaction. If then order of reaction is equal to m plus n. And if it is an elementary reaction, that means which complete in a single step, then according to rate law, R is equal to K, molar concentration A to the power A into B to the power B. That means here order of reaction is equal to A plus B. Mark that. So from this expression it is clear that order of a reaction is defined as the sum of the powers, the sum total of the powers of the molar concentration of reactant species which is represented in a rate law expression. I repeat again. The order of a reaction may be defined as the sum of the molar concentration, sum of the powers of the molar concentration of the reactant species which is represented in rate law expression. This value may be positive, may be negative, may be zero or may be fraction. Its value depends upon temperature. For a particular reaction at a particular temperature, that means we calculate the order not simply by seeing the expression rate, simply by the balanced chemical reaction. Because, I repeat again, it is based upon the experimental phenomena. For elementary reaction, we calculate by applying law of mass action is equal to rate law. But for a complex reaction, means the reaction which proceeds number of steps, then we calculate the order of a reaction as a whole. That means for each step order of reaction has no mean. Then we go through the characteristics of order of reaction. 3 to 4 points are there. Characteristics of order of reaction. It is an experimental phenomenon. No one able to observe calculate the order of a reaction by observing simple the mathematical expression balanced chemical reaction. Its next point, its value may be positive, negative, zero or fraction. The order of a reaction may be positive, negative, zero or fraction. In general, its value never exceeds 3. Rarely, rare case is there, or in general, its value never exceeds 3. It is an experimental concept. It is independent of initial concentration. It is independent of initial concentration of reactants. It is represent as a whole for a simple as well as for a complex reaction. I repeat again. That means the reaction which proceed a number of steps, then we calculate the order of reaction as a whole. Never we are able to calculate the order of reaction of each step. And most important thing is that it is an experimental phenomena. Or no one is able to calculate the order of a reaction by simply observing a balanced chemical reaction. Next we discuss about the types of order of reaction. One important point is there, that is, its value may be positive, 0, fraction. So depending upon this one, there are different type of order of reaction. These are zero order reaction. I repeat again, types of order of reaction. That is zero order reaction, first order reaction, pseudo first order reaction, second order reaction, third order reaction, fractional order reaction. We discuss one by one. First one is zero order reaction. So what do you mean by zero order reaction? It is the type of reaction in which there is no change. The molar concentration of reactant does not affect the rate of reaction. Suitable examples are there. That is, photochemical combination of hydrogen with chlorine. So the example is there. Photochemical combination of H2 and Cl2, that is H2 plus Cl2 in present sunlight. Photochemical combination of hydrogen and chlorine over the surface of water, 2HCl. It is example of zero order. I repeat again, it is a type of reaction in which the molar concentration of reactant does not affect the rate of reaction. Another example is there. Decomposition of ammonia over the surface of platinum. Another example. Decomposition of ammonia over the surface of platinum, that is 2NH3 over the surface of platinum, heat N2 plus 3H2. Another example is there. Dissociation of hydrogen iodide on the surface of gold. Another one example is there. That is dissociation of hydrogen iodide over the surface of gold. That is 2Hi over the surface of gold, H2 plus I2. These are some examples of zero order reaction. Next switch over to first order reaction. Next is first order reaction. It is a reaction in which only one reactant concentration term involved change during the rate of reaction. For example, decomposition of nitrogen pentoxide. Example, decomposition of N2O5, that is N2O5 heat N2O4 plus half O2. Then another example is there, decomposition of ammonium nitrite NH4NO2, that is NH4NO2 break down to N2 plus 2H2O. All the natural and artificial radioactive disintegration. Another example is there. All the natural and radioactive decay, DECAY, decay or disintegration follows first order kinetics. Next we switch over to pseudo first order, false first order reaction. Next we discuss about pseudo first order reaction. What do you mean by false first order? Means by looking the reaction, it is clear that it belongs to a second order reaction. Means two reactant species involved in the reactant reaction. So two reactant concentration change during the rate of reaction. But actually there is one concentration or one reactant concentration term changes. That means generally one of the reactant species whose concentration, whose amount is taken so large that what sort of a change in concentration is not calculated, that is neglected. So that is known as pseudo first order reaction. For example, inversion of sugar cane. Suitable example, inversion of cane sugar. That is C12H22 O11 plus water give rise to C6H12O6 plus C6H12O6. It is sucrose, it is glucose, it is fructose. From this reaction it is clear that two reactant species is there, but according to rate law expression, that is, it is sucrose power 1 H2O power 0. Therefore, order of reaction is equal to 1. That means the hydrolysis, that means water is present so large that what sort of change in concentration cannot be calculated. So it is neglected. So only one concentration term change. That's why seems to be second order, but actually it is a first order. That's why it is known as a false first order or a pseudo first order reaction. Another example also there. That is acid hydrolysis of ester. Acid hydrolysis of ester, that is CH3COOC2H5 plus H2O in presence of mineral acid CH3COOH plus C2H5OH. Its name is ethyl acetate, that is ester. It is acetic acid. It is ethyl alcohol. Same reason is there. Here, according to rate law expression, R is equal to, that is ester to the power 1, water to the power 0, that is order of reaction is equal to 1. So seems to be second order, but actually it is a first order. That's why it is known as a false first order or pseudo first order. Next, switch over to second order reaction. Next is second order reaction. It is a type of reaction in which the concentration of two reactant species involved during the reaction. That's what is known as the second order reaction. For example, alkaline hydrolysis of ester. Example is second order reaction. There is alkaline hydrolysis of ester. That is CH3COO-C2H5 plus NaOH give rise to CH3COO-Na plus C2H5OH. It is known as ethyl acetate, that is ester. It is sodium acetate. It is ethyl alcohol. Another example is there, that is decomposition of hydrogen iodide. Another example, decomposition of hydrogen iodide, that is 2Hi give rise to H2 plus I2. These are suitable examples of second order reaction. Next we discuss to third order reaction. That is third order reaction. Type of reaction in which three reactant species involved in the rate of reaction, three reactant species concentration change, or sum of the molar concentration of the reactant species according to rate law expression is 3. Suitable examples is there. That is oxidation of sulfur dioxide. That is suitable example. Oxidation of sulfur dioxide, that is formation of sulfur trioxide. It is R, according to rate law expression, R is equal to SO2 power 2, O2 power 1, that means order of reaction is equal to 3. Similarly, oxidation of nitrogen monoxide, that is nitric oxide, that is 2NO plus O2 give rise to 2NO2. Here also R is equal to, that is R according to rate law expression K NO power 2 O2 power 1, that means order of reaction is equal to 3. These are some suitable examples of third order reaction. Next is about to fractional order reaction. Next one is fractional order reaction. Means these are the reaction whose sum of the molar concentration of reactant species is a fraction. That means as it is an experimental phenomenon, no one, I repeat again, no one able to recalculate the order of a reaction. It is based upon the experimental phenomena. Suitable example is decomposition of acetaldehyde. Suitable example, decomposition of acetaldehyde. Equation is CH3CHO break down to CH4 plus CO. Another example, formation of hydrogen bromide. Formation of hydrogen bromide. So here, before going to this one, according to rate law expression, R is equal to K, molar concentration of acetaldehyde to the power 3 by 2. That means order of reaction is equal to 3 by 2 or 1.5. Similarly, another example is there. Formation of hydrogen bromide. That means mathematical expression, that is H2 plus Br2 give rise to 2HBr. Then according to rate law expression, R is equal to K H2 Br2 to the power 1 by 2, it is 1. Therefore, order is equal to 1 plus 1 by 2, that is 3 by 2 or 1.5. These are some examples of fractional order reaction. So, what is order of reaction? Characteristics of order of reaction, types of order of reaction. Then we go through the unit of rate constant. Next, we discuss about unit of rate constant. As already we covered, that is, the unit of rate constant depends upon the order of reaction. Unit of rate constant. That is, unit of rate constant depends upon the order of reaction. So for nth order, the unit of rate constant is represented as that is K is equal to moles per liter to the power 1 minus n second inverse. Mark that. I repeat again. Where n is known as the order of reaction. So by putting n is equal to 0, that is for 0 order. Mark that. Unit of K is equal to moles per liter per second. Then n is equal to 1, that is for first order reaction. Unit of K is equal to second inverse. Because here it is 1, 1 minus 1, 0, everything power 0 is equal to 1. Next, n is equal to 2, that is for second order reaction. Unit of K is equal to moles per liter to the power minus 1 second inverse. That is liter mole inverse second inverse. Similarly, we calculate for the third order, fourth order, and for nth order, the unit of rate constant, that is moles per liter, that is concentration to the power 1 minus n dot second inverse. So for the gaseous species, if the reactant becomes to gaseous one, then its concentration instead of moles per liter will be represented in partial pressure, that is atmospheric pressure. In that case, unit of K is equal to atmospheric pressure to the power 1 minus 1 and the second inverse. So from this mathematical expression, we observe one important thing is that for a zero order reaction, the unit of rate of reaction is equivalent to unit of rate constant. And another one important thing is that for first order reaction, The unit of rate constant for fast order reaction is independent of the molar initial concentration, molar concentration of the reactant. So basing upon this data, let us solve one or two problems. Next we discuss one or two problems basing upon this data. First question. According to rate law expression, that is R is equal to K, A to the power 1 by 2, B to the power 3 by 2, bit 1, bit 2, R is equal to K, A to the power 1 by 2, B to the power minus 3 by 2. It is the question. Question is calculate the order of individual one and as a whole for the reaction. How we solve? Mark that. First we solve the bit 1. Mark that. With respect to A, if we compare only A, with respect to A, that means order of reaction is equal to half. With respect to B, individual one, the order of reaction is equal to 3 by 2. As a whole, for the total reaction, order of reaction is equal to 1 by 2 plus 3 by 2. That is 2. Similarly, the second bit, mark that. With respect to A, the order of is 1 by 2. With respect to B, order is minus 3 by 2. So as a whole, order is 1 by 2 minus 3 by 2. That means minus 1. I repeat again. This value order of reaction may be positive, may be negative, may be 0 or fraction. It is one type of problem. Switch over to another type of problem. Next type of problem. According to rate law expression, data is given, that is R is equal to K, A, B, C power 2. It is the rate expression according to rate law. It is given in the question. Bit 1 is calculate the order of reaction. Calculate the order of reaction. Calculate the rate of reaction. Rate of reaction. If molar concentration of B, if molar concentration of C increases 2 times, and point 2 decreases if the molar concentration of B decreases to 1/2. Mark the 2 bit is there. We have to predict bit 1 answer. What we observe? If the molar concentration of reactant species C is double 2 times. So before that, let us consider the molar concentration of A is A moles per liter. A moles per liter. Molar concentration of B is B moles per liter. Molar concentration of C is C moles per liter. Then the rate expression, then we calculate the rate expression, that is R is equal to K, A, B, C square, equation 1. Okay. So data is given, the molar concentration C is double. So that is R1 is equal to K, A, B, that is double means 2C square. So is equivalent to 4K, A, B, C square. That means 4R. So from this expression it is clear that rate of reaction increases 4 times. Move to the second one. The second one, what is the second one? The molar concentration of B reduced to half. That means, mark that, R2 is equal to K, A, B by 2, C square. Or is equal to 1 by 2, K, A, B, C square. Is equivalent to half R1. So from this expression it is clear that the rate of reaction becomes half if the molar concentration or reactant species, that is B, is reduced to